Greetings and welcome to a new video about an induction motor example. This is our example number 2. In this example we will again work another problem in great detail. So let's look at the problem. We have a 6-pole 60 Hz 3-phase Y-connected induction motor with the following parameters. This is the part for the stator and this is the part of the rotor which will be reflected on the stator part, and this is the magnetization reactance. This will be used later on in our equivalent circuit. This motor here is used to drive a fan which requires a shaft power of 7.5 kilowatts at this speed, 1150 RPM. The question now here is calculate the required terminal voltage, which is actually the line to neutral voltage, to achieve this operation. So let's look at their solution step by step. And again we start with a model, and this model is the per phase model. So we have a 3-phase system or 3-phase machine, but we work out the problem using just one phase and then multiply the required parameters by 3, and that will then allow us to work it in step by step. Okay. Terminal voltage is in this case just the phase voltage, and phase voltage is what you actually see here. So the phase voltage what you here see will be then of course given in RMS will be equal to this value. So we will need to calculate this using the current flowing here and also the value of the total impedance here, which is actually shown here. So this is the total impedance between these two nodes. Okay, so the total impedance seen between these two nodes is the series combination of these two elements, RS and JXS, which is actually shown here, plus the parallel combination of these two branches. But we know from the example given information that this is an open, so we can say this is a complete series connection. And it's actually then the following condition. This will then go because that's infinite, and then I have the expression using just 4 elements. Of course we see here 5 elements which will designate this as a load specifically, but if you combine this, so R sub R prime and this one, you will get R sub R prime over S. This is just add these together, you will get this. So if I now work it out using the given values for my parameters here, I will have this expression. And what you see here directly is we need the slip because that is the unknown here. So we cannot calculate the total impedance yet. Now for the slip we need the synchronous speed, and synchronous speed omega sub s is given by this expression which has the number of poles and also the electrical frequency in radians per second, of course. The number of poles here is 6, and also the radian frequency is given here then as cyclic frequency here in hertz. So we need to work it out in F, and if I now substitute the given values for P, capital letter P is 6, and F sub A is here 60, I will have 125.7 radians per second, or if you convert it in another unit, RPM, will be 1200. Okay, now going to the slip. Slip is given by this expression, which is then a synchronous speed minus the rotor speed over synchronous speed. Or if you want to have it in a different unit, RPMs, then exact same expression can be used, but then using the N sub S minus NR over N sub S. Now we know what the rotor speed must be. It's 1150 RPM. We know the synchronous speed, so we can calculate what the slip must be. Just use the values given in this information. 1 over 24 will be our slip. So I know the necessary information to calculate my total impedance. So total impedance will be then this, and if I now work it out, you will have this expression, and if I combine now the real parts, so 0.2 and a 2.4 together, and also the 2 J's here, I will get 2.6 plus J 1.7 ohms. And if I now convert this into the polar representation, I will then see directly my amplitude. And how do I do this? You will take the square root of each of this squared, add them up, and you will have this. And the phases here, in this case, 33 degrees. So 3.11 as our amplitude for our total impedance. So we know this, but still we don't know what the phase current here is. So for that we need the developed power, and we know what the developed power is because that's the shaft power. So we can use this information to come to the current here. But actually the current what is flowing for the developed power is this current, which is already shown here. So this is then again 3 times to go from 1 phase to 3 phase. This is the representation of load, and this is the current flowing through that load. So it's actually IR times R, so I squared times R. And we have, of course, again 3 times to go from 1 phase to 3 phase. If I now rewrite this such that I know what the current value is for a given specific shaft power or developed power, I have then this expression, again 7,500, 1 over 24 for my slip, and the rest of the values for 0.1 for this parameter. And I will have then 32.97 amperes in RMS. That's what the values for this current here. But since this is an open, so there's no current flow in here, this is also the same value. So I can say the phase current here is also this current which we have calculated. Now we are now very close to the final value because I know this as a magnitude. I also know the value of this as a magnitude because it's already shown here, 3.11. I can then say, using again Ohm's law here in this expression, I have 102.5 volts RMS. And that is the phase voltage. So actually for the Y connection, you will have actually 3 sources, and one of the source from the terminal to the neutral will have this value. From one terminal to another terminal, you need to multiply this by square root of 3 in order to get to the line-to-line voltage, which is different than line-to-neutral voltage. Okay, this concludes this example number 2 about an induction motor, where we have calculated the required phase voltage for this specific situation for a fan which requires a shaft power of 7.5 kilowatts with this speed. If you have any questions about this problem, please let me know and I will try to answer them as soon as possible. See you next time and take care.